Find somewhere comfortable. You don't need to sit up straight or keep your eyes open. You don't need to hold on to any of this. Just let the words come to you the way light comes through a curtain, soft, indirect, not asking anything of you. We're going somewhere quiet tonight, somewhere wide and high and ancient. We're going to look at the sky. Not the sky as backdrop, not clouds as decoration, the actual sky, the invisible machinery of it, the patient chemistry, the geometry that has been working above every human life ever lived, whether or not anyone was watching. If today was hard, you can set it down now. Whatever you carried through the hours since morning, the weight of it, the unfinished edges of it, you don't need to bring it here. The sky doesn't carry the day's trouble. It just keeps moving, slowly. Tonight, we're going to follow water on one of its oldest journeys, from the surface of an ocean to the high cold air, from an invisible molecule to a visible cloud, from a single droplet to a rainstorm, and from a rainstorm to the deep, patient cycle that has been running on this planet for 4 billion years. We'll meet the man who gave clouds their names, and we'll understand why those names spread across every language on Earth within a decade of being written down. We'll go inside a single cloud droplet and understand what holds it together and what finally makes it fall. You don't need to remember any of this. You don't need to follow closely. If you drift somewhere in the middle, that's exactly where you're supposed to be. The sky will still be there when you surface again, and so will we. Take a slow breath. Let the weight of the day begin its long settling. We begin, as all good things do, with a name. Before the year 1803, the sky had no grammar. This is worth sitting with for a moment, because it seems strange to us now. We live in a world so thoroughly named and mapped and catalogued that it's difficult to imagine a time when something as vast and obvious as a cloud had no agreed word for its shape, no system for its type, no way for a scientist in England to describe to a scientist in Germany precisely which formation had appeared before the rain came. Clouds were spoken of the way moods are spoken of, vaguely, impressionistically, with words that belonged to no shared language of science. They were considered, by the natural philosophers of the 17th and 18th centuries, to be fundamentally beyond classification, too changeable. They dissolved and reformed and shifted from one shape into another while you watched them, and so the general view was that clouds were the atmosphere's way of resisting the orderly ambitions of science. Into this unnamed sky came a quiet, methodical man named Luke Howard. Howard was not a professional scientist, at least not in the way we would understand the term today. He was a manufacturing chemist who ran a business producing pharmaceutical chemicals in London. He had grown up in the late 18th century, educated partly by Quakers, and had absorbed the careful, patient, observational habits of that tradition. He was also, from a young age, intensely curious about the sky. He lived for a period in Tottenham, then a village north of London, and he spent his evenings watching the clouds above the fields and the rooftops, keeping notes, drawing what he saw, trying to find the patterns that everyone else had dismissed as non-existent. What Howard noticed, and what turned out to be his crucial insight, was that clouds might be infinitely variable in their details, but they were not infinitely variable in their fundamental forms. There were, he believed, a small number of distinct types, not fixed objects, but recurring shapes, recurring structures, recurring ways that water and air organized themselves in the atmosphere. The same forms appeared again and again in different places, in different seasons, at different times of day. They were not random. They were, in some deep sense, lawful. In 1803, he presented his findings to the Ascasian Society, a gathering of amateur natural philosophers in London, and then published them as a short essay titled, simply, On the Modification of Clouds. It was one of the most quietly consequential scientific papers of the 19th century. Howard proposed 3 primary cloud forms, and he named them in Latin. This choice of language was deliberate, and it was probably the single most important decision he made. Latin was nobody's mother tongue, which meant it was nobody's property. It belonged equally to a German meteorologist, a French sailor, an Italian shepherd watching the sky above the hills. When Howard chose Latin, he chose universality. His 3 founding categories were cumulus, stratus, and cirrus. Cumulus from the Latin for heap or pile. The rounded, towering, cauliflower-shaped clouds that build upward from a flat base, the ones we draw as children, white and solid, looking against a blue sky. Stratus, from the Latin for layer, the flat, horizontal sheets of cloud that spread across the sky like grey linen, bringing dull days and drizzle, the clouds that make a winter morning feel like the sky has simply lowered itself onto the earth. And cirrus, from the Latin for a curl of hair, the high, thin, wispy filaments that drift at great altitude, drawn out by high winds into delicate parallel streaks, the clouds that look like someone has dragged a fine brush lightly across the blue. To these 3, Howard added a 4th category, nimbus, from the Latin for rain cloud or halo, used to describe the heavy, dark, rain-bearing cloud that produces sustained precipitation. And he described intermediate and compound forms, cirrostratus, which appears as a thin sheet high in the sky through which the sun shines with a characteristic milky haze. Cirrocumulus, small, rounded puffs arranged in rows at high altitude, the so-called mackerel sky. And cumulonimbus, the great vertical tower that he recognized as a distinct and powerful form, rising from low in the atmosphere toward the highest levels, capable of producing violent weather. What made Howard's system work, beyond the elegance of the Latin names, was its underlying logic. He wasn't classifying clouds by their color, or by the weather they produced, or by the time of year they appeared. He was classifying them by their physical structure, by the way air was moving within them and around them. A cumulus cloud exists because air is rising vertically. A stratus cloud exists because air is moving horizontally, in stable layers. A cirrus cloud exists at such high altitude, where temperatures are so low that it is made not of liquid water droplets but of ice crystals, drawn into filaments by the wind. Howard didn't know the full physical reasons for these forms in 1803. The atmospheric science to explain them wouldn't develop for another century, but his categories turned out to map almost perfectly onto the underlying physics. The system spread with remarkable speed. Within a decade, meteorologists across Europe were using Howard's Latin terms. The German poet and polymath Johann Wolfgang von Goethe, who was in his 50s when Howard published his essay and who had spent a lifetime observing nature with the eye of both a scientist and an artist, was so moved by what Howard had done that he wrote a cycle of 4 poems in his honor. The poems are titled after Howard's cloud types, stratus, cumulus, cirrus, nimbus, and they treat the classification of clouds not as a dry taxonomic exercise but as a profound act of attention, a way of seeing the sky that was also a way of understanding it. Goethe sent Howard a copy of the poems, along with a personal letter of admiration. Howard, the quiet Quaker chemist from Tottenham, had given the sky a language, and one of the greatest minds in Europe had written poetry in gratitude. The system Howard built in 1803 has never been abandoned. It has been extended, refined, and reorganized. The World Meteorological Organization now recognizes 10 basic cloud genera, all descended from Howard's original terms, but the core vocabulary remains: cumulus, stratus, cumulus, stratus, cumulonimbus. These are words used by every meteorologist on Earth today in exactly the sense Howard intended them. And the framework is still growing. In 2017, for the first time in 67 years, the World Meteorological Organization added a new cloud type to the official International Cloud Atlas. It was called asperitas, from the Latin for roughness, and it describes a strange and beautiful formation in which the underside of a cloud layer becomes turbulent and wave-like, the surface broken into irregular, chaotic undulations that look, from below, like the surface of a disturbed sea viewed from underwater. The Cloud Appreciation Society, a global organization with hundreds of thousands of members, had campaigned for years for Asperitas to be officially recognized. When it finally was, the announcement was greeted with something that can only be described as joy, which tells you something about what clouds have come to mean to the people who watch them. Luke Howard gave us the language, and we have never stopped using it to speak. The sky above Tottenham in 1803 was the same sky it always had been. But after Howard looked at it and wrote down what he saw, it became a different kind of thing. A named thing. A knowable thing. A thing that could be understood, not just admired. That understanding begins with a single molecule of water rising from the surface of the sea. The ocean is not still, even on the calmest day. At its surface, water molecules are in constant motion, vibrating and jostling against one another, and the energy of that motion is not evenly distributed. Some molecules are moving faster than others. This is always true of any substance above absolute zero temperature. The molecules within it have a range of speeds, a distribution of energies, and at any given moment a small fraction of the molecules at the surface have enough energy to do something the others cannot, to break free from the liquid entirely and escape into the air above as individual gas molecules. This is evaporation. It is happening continuously in every ocean and lake and river and puddle on the planet at every hour of every day, and it is the engine that drives everything else we are going to talk about tonight. A water molecule in the gas phase is called water vapor, and the air around us always contains some of it. How much it can contain depends almost entirely on temperature. Warm air can hold considerably more water vapor than cold air, not because warmth creates more room in some physical sense, but because the energy of warm air molecules is higher, which means vapor molecules are more likely to stay in the gas phase rather than collide and stick together. At 20 degrees Celsius, a cubic meter of air can hold roughly 17 grams of water vapor before it becomes saturated. At 30 degrees, that rises to about 30 grams. At 10 degrees, it falls to around 9. Temperature is the key, and temperature is what governs everything that follows. Now imagine a parcel of warm, moist air sitting close to the ocean surface on a summer afternoon. The sun has been heating the ocean and the air above it for hours. This parcel of air is warmer than the air around it, which means it is less dense than the air around it, and less dense things in a gravitational field float upward. This is the same principle that lifts a bubble of warm gas in a lava lamp or carries heat upward from a radiator in a cold room. The warm air parcel begins to rise. As it rises, something important happens. The atmosphere is not uniform in pressure from bottom to top. It is compressed by its own weight, so pressure decreases with altitude. At sea level, the weight of the entire column of atmosphere above presses down with considerable force. A kilometer higher, there is less atmosphere above, so the pressure is lower. 2 kilometers higher, lower still. The rising air parcel, as it moves into this region of lower pressure, expands. Its molecules spread out and occupy more space. Here is the crucial step, and it is worth following carefully. When a gas expands, it does work against the surrounding air. It has to push the surrounding air out of the way to make room for itself. That work requires energy. The energy has to come from somewhere, and the only place it can come from is the internal kinetic energy of the gas molecules themselves. So as the air parcel expands, its molecules slow down slightly, and the temperature of a gas is simply a measure of the average speed of its molecules. Slower molecules mean a lower temperature. The air parcel cools. This process, cooling by expansion without any heat being exchanged with the surroundings, has a specific name. It is called adiabatic cooling, from the Greek word meaning impassable, referring to the fact that no heat passes in or out. The air parcel is not losing heat to the sky around it. It is not radiating away energy. It is simply expanding, and that expansion itself is the cooling mechanism. This is a fundamental consequence of how gases behave, and it is one of the most important physical processes in all of atmospheric science. The rate at which unsaturated rising air cools adiabatically is remarkably consistent, roughly 10 degrees Celsius for every kilometer of altitude gained. Meteorologists call this the dry adiabatic lapse rate. So a parcel of air that starts at, say, 20 degrees Celsius at the surface will cool to about 10 degrees after rising 1 kilometer and to around 0 degrees after rising 2 kilometers, and so on. This is not an approximation or a rule of thumb. It follows directly from the physical properties of air, and it holds with impressive reliability across the atmosphere. As the air parcel rises and cools, its water vapor content stays the same. The same number of water molecules are present, but the capacity of the air to hold that vapor is falling because the air is getting colder. At some point, the air parcel will have cooled to the temperature at which it is exactly saturated, where it is holding precisely as much water vapor as it is able to hold at that temperature. This temperature is called the dew point. It is the temperature at which, if cooling continues, water vapor must begin to condense into liquid water. The altitude at which the rising air parcel reaches its dew point is the altitude at which the cloud base forms. This is why the bases of cumulus clouds on a warm summer day are so remarkably flat and level. They mark a precise altitude, the lifting condensation level, where the temperature of the rising air has fallen to meet its dew point. You can sometimes see a whole field of cumulus clouds lined up across the sky, each with its flat base at exactly the same height, because the air beneath them all started at roughly the same temperature and humidity, and all reached their dew point at the same altitude. The cloud base is not arbitrary. It is a physical threshold made visible. Now, at the molecular level, what actually happens at that threshold? When the air reaches saturation and begins to cool further, the water vapor molecules start to condense. But condensation does not happen spontaneously in mid-air, with water molecules simply clumping together out of nothing. A tiny cluster of water molecules, forming from nothing in clean air, has an extremely high surface area relative to its volume, and maintaining that curved surface requires energy. Very small droplets are thermodynamically unstable. They tend to re-evaporate almost immediately after forming. This is where one of the most beautiful and consequential facts in atmospheric science comes in. Every cloud droplet, every single one of the billions upon billions of tiny droplets that make up any cloud you have ever seen, forms not from pure water vapor condensing alone, but around a pre-existing microscopic particle, a speck of dust, a fragment of sea salt crystal, a grain of pollen, a tiny particle of volcanic ash, even, in some cases, a living bacterium. These particles are called cloud condensation nuclei, and they are the seeds around which clouds grow. The reason they work is elegant. A flat or gently curved surface is far easier to wet than a curved one. A water molecule landing on a particle surface can bond to it without the enormous energy cost of creating a new curved liquid surface from nothing. The particle lowers the energy barrier to condensation, allowing water molecules to begin accumulating on its surface at temperatures and humidity levels where they would otherwise remain as vapor. Once a few molecules have stuck, the surface grows, the curvature decreases, and condensation becomes progressively easier. The droplet grows. The typical cloud condensation nucleus is extraordinarily small. Most are somewhere between 1/10 of a micrometer and a few micrometers across, where 1 micrometer is 1/1,000,000th of a meter. A human hair is roughly 70 micrometers wide. These particles are invisible to the naked eye, and yet without them, the sky would be almost cloudless. Even what we call clean air, far from any city or industrial source, contains thousands of these particles per cubic centimeter. Sea salt flung into the air by breaking waves, mineral dust carried on the wind from dry land, organic particles released by forests and grasslands. The atmosphere is never truly empty, It is always seeded, always ready. And once condensation begins, the droplet grows, slowly at first, then more quickly as more and more water molecules join it. The cloud becomes visible, not because a single large droplet has formed, but because billions of tiny droplets have formed simultaneously, each one catching and scattering light. A cloud is not a solid object and not a gas. It is a suspension, a vast population of liquid droplets, each one typically between 5 and 20 micrometers across, small enough and light enough to be kept aloft by the gentle upward currents of air within the cloud itself. The cloud you see from the ground is the visible evidence of an invisible process, the atmosphere reaching its dew point, and water finding, in the tiniest particles of the world, the surfaces it needs to begin its transformation. Take a single breath of the air in this room, hold it for a moment, or imagine holding it. Inside that breath, right now, there are thousands of microscopic particles, not harmful, not unusual, simply present, as they have always been in every breath of air ever drawn by any living thing on this planet. Some of them are fragments of mineral dust carried on the wind from distant deserts, perhaps the Sahara, perhaps the Gobi, perhaps a dry riverbed, somewhere you will never visit. Some are tiny crystals of salt, each one the dried remnant of a sea spray droplet that evaporated somewhere over the Atlantic or the Pacific, leaving its mineral skeleton behind to drift inland on the wind. Some are fragments of pollen, the reproductive particles of grasses and trees, each one a precise geometric structure, a tiny sphere or disk or star shape with a surface chemistry evolved over millions of years. And some, in ways that are still being actively studied, may be living bacteria, riding the air currents of the lower atmosphere as a means of dispersal. These are cloud condensation nuclei, and their chemistry matters enormously, not just whether they are present, but what they are made of, how large they are, and how they interact with water. The most effective cloud condensation nuclei are what chemists call hygroscopic, from the Greek for water. A hygroscopic particle is one that has a strong chemical affinity for water, meaning water molecules are drawn to its surface and bond to it readily. Sea salt is one of the most hygroscopic substances found naturally in the atmosphere. A sea salt crystal doesn't just provide a passive surface for condensation. It actually begins to absorb water vapor at relative humidities well below 100%, sometimes as low as 70 or 80%. The salt dissolves into the condensing water, forming a small droplet of brine, which then continues to grow as more water vapor condenses onto it. This means that in marine air over the ocean, clouds can begin to form earlier and more easily than in drier continental air, because the sea salt nuclei are so efficient at capturing water. Mineral dust particles from the continents are less hygroscopic than sea salt, but they are present in enormous quantities, and they are large enough to serve as effective nuclei. After major volcanic eruptions, when the atmosphere is seeded with fine ash particles, the nuclei count in the lower atmosphere can increase dramatically, sometimes altering cloud cover over large regions for months at a time. Pollen grains are interesting because they are large, typically between 10 and 100 micrometers across, which is enormous compared to most nuclei, and they have complex, chemically active surfaces that interact with water in ways scientists are still working to understand fully. Some pollen species appear to be particularly effective at triggering rainfall in certain conditions, and there is ongoing research into whether the seasonal release of pollen might influence precipitation patterns in forested regions. The bacteria are perhaps the most intriguing. Certain species of bacteria, particularly those that live on the surfaces of plants, produce proteins on their outer membranes that are extraordinarily effective at initiating ice formation. These bacteria can be carried into the atmosphere when plants are disturbed by wind or rain, and once airborne they can serve as nuclei, not just for liquid cloud droplets, but for ice crystals at temperatures far warmer than ice would normally form. This is called bioprecipitation, and while it remains an active area of research, some scientists believe that the life cycle of certain plant-associated bacteria has evolved partly to exploit this pathway, using the atmosphere as a vehicle for dispersal, riding precipitation back down to new surfaces. Now we mentioned ice, and it is time to talk about one of the more counterintuitive facts in all of atmospheric science. Water, as you know, freezes at 0 degrees Celsius under normal conditions, but in clouds the rules are different. Cloud droplets can remain liquid at temperatures far below freezing, sometimes as low as -40 degrees Celsius, without turning to ice. This state is called supercooled water, and it is not a rare or exotic condition in clouds. It is extremely common. Much of the cloud cover over the mid-latitude at any given moment contains supercooled liquid water. Why doesn't it freeze? The answer goes back to the same surface energy problem we encountered with condensation. For a liquid droplet to freeze, it needs to form a tiny crystal of ice within itself, a nucleus of solid water around which the rest of the liquid can organize. But creating that first tiny ice crystal requires energy, because the surface of the ice crystal has a higher energy than the bulk liquid around it. In a large body of water, a lake, a glass, there are always impurities and surfaces present that can serve as ice nucleation sites, and so freezing happens readily near 0 degrees. But in a tiny, pure cloud droplet with no impurities, the energy barrier to forming that first ice crystal is high enough that the droplet can remain liquid, well below zero, suspended in a state of unstable equilibrium, waiting. The smaller and purer the droplet, the lower the temperature it can reach before freezing spontaneously. Laboratory experiments have shown that extremely small, extremely pure water droplets can remain liquid down to about -40 degrees Celsius, at which point the thermal energy of the molecules falls so low that ice formation becomes inevitable even without a nucleus. But in the real atmosphere, most supercooled droplets freeze before reaching that extreme because they encounter particles that serve as ice nuclei, mineral dust, biological particles, or certain clay minerals that happen to have surface structures closely matching the crystalline lattice of ice. These ice nucleating particles are rarer than cloud condensation nuclei, which is why supercooled water is so common. There are plenty of seeds for liquid droplets, but far fewer seeds for ice crystals. This distinction between the abundance of liquid droplet nuclei and the scarcity of ice nucleating particles turns out to be critically important for how precipitation forms, as we will see in the next chapter. But it also has a human dimension that is worth pausing on. Since the Industrial Revolution, and particularly since the expansion of road transport and industrial manufacturing in the 20th century, human activity has been adding enormous quantities of new particles to the atmosphere: soot from diesel engines, sulfate particles from the burning of coal, fine mineral particles from agricultural activity. These anthropogenic, human-generated aerosols are cloud condensation nuclei, and their addition to the atmosphere has measurable effects on clouds. Here is the mechanism, and it is subtle. Imagine a cloud forming in clean marine air, where there are relatively few condensation nuclei available. The available water vapor is distributed among a relatively small number of droplets, so each droplet can grow fairly large, perhaps 15 or 20 micrometers across. Now imagine the same cloud forming in air that has been enriched with soot particles from a city upwind. There are now far more nuclei available, so the available water vapor is shared among a much larger number of droplets. Each individual droplet ends up smaller, perhaps 5 or 8 micrometers across. The total amount of liquid water in the cloud is roughly the same, but it is divided among many more, smaller droplets. Smaller droplets scatter sunlight more effectively than larger ones, A cloud made of many small droplets therefore appears brighter, more reflective than one made of fewer large droplets. This is called the first aerosol indirect effect, or sometimes the Twomey effect, after the researcher who first described it clearly in the 1970s. From a climate perspective, brighter clouds reflect more of the sun's energy back into space before it can warm the surface, which produces a cooling effect. There is also a second effect. Smaller droplets are less likely to collide and coalesce into raindrops, which means the cloud lives longer before precipitating out. Clouds that last longer cover the sky for more hours, reflecting more sunlight over a longer period. This is the second aerosol indirect effect, sometimes called the cloud lifetime effect. Both of these effects produce cooling, and they partially offset the warming caused by greenhouse gas emissions. But here is the difficulty. The magnitude of these effects is extremely uncertain. Climate scientists can observe that polluted clouds tend to be brighter and longer-lived than clean ones, but quantifying exactly how much cooling this produces globally and how it will change as pollution levels change in different parts of the world requires modeling cloud microphysics at a level of detail that remains beyond current computational power. The aerosol indirect effect is consistently identified as one of the largest sources of uncertainty in projections of future climate. We know the direction. We don't know the size. What we do know is this. Every cloud in the sky tonight, whether forming over a clean ocean or over an industrial city, is a product of the particles it carries. The seeds of clouds are everywhere. In desert dust, in sea spray, in forest air, in the exhaust of engines. And the chemistry of those seeds shapes the clouds themselves, their brightness, their lifetime. And whether or not they will eventually produce rain, the sky is not empty. It is full, invisibly full, of the world below it. A cloud droplet is very small. This seems like a modest observation, but the smallness of a cloud droplet is genuinely extreme, and it matters enormously for what happens next. A typical cloud droplet is about 10 to 20 micrometers across roughly a fifth of the width of a human hair. A raindrop, the kind that falls on a window or a pavement, is typically about 2 millimeters across, though it can be larger. That is a difference in diameter of roughly 100 to 1, which means a difference in volume, since volume scales with the cube of diameter of roughly 1 million to 1. A single raindrop contains about 1 million cloud droplets worth of water. The question of how that gap is crossed is one of the deepest and most practically important questions in atmospheric science. It is not obvious, and it is not simple. A cloud droplet does not simply grow molecule by molecule from 10 micrometers to 2 millimeters by condensation alone. The rate of condensational growth, the rate at which individual water vapor molecules land on the droplet surface and add to it, is rapid when the droplet is very small, but it slows dramatically as the droplet grows. This is because the surface area of the droplet increases as it grows, but the rate at which vapor arrives at the surface is limited by how quickly vapor molecules can diffuse through the surrounding air. The mathematics of diffusion-limited growth means that condensation alone can bring a droplet up to about 20 or 30 micrometers fairly quickly, but beyond that, condensational growth becomes frustratingly slow. To grow a droplet from 30 micrometers to 2 millimeters by condensation alone would take far longer than clouds actually survive. Something else must be happening. Two things, in fact, depending on the temperature of the cloud. In warm clouds, clouds where the temperature throughout is above 0 degrees Celsius, common in the tropics and in summer at lower latitudes, the dominant process is called collision coalescence. The principle is straightforward, but the details are rich. Within a cloud, droplets are not all the same size. Even if they all started from similar nuclei in similar conditions, small differences in the sizes of their nuclei and small differences in the local humidity they experienced as they formed mean that after a short time there is a distribution of droplet sizes present. Some droplets are slightly larger than average, some slightly smaller. larger droplets fall faster through the air than smaller ones. This is a consequence of the balance between gravity and air resistance. A larger droplet has more mass pulling it down and a larger cross-section creating drag, but the mass scales with the cube of the radius, while the drag scales roughly with the square, so larger droplets win the race and fall faster. A droplet of 20 micrometers falls at roughly 2 centimeters per second. A droplet of 40 micrometers falls at about 16 centimeters per second, 8 times faster. As the larger droplets fall relative to the smaller ones, they sweep through the population of smaller droplets below them, and when they collide, they sometimes merge, coalesce into a single larger droplet. It is a runaway process, a positive feedback loop, and it can carry a droplet from 20 micrometers to 2 millimeters in perhaps 20 minutes to half an hour, which is consistent with the timescale on which we observe warm clouds to produce rain. The efficiency of this process depends on several factors. The relative sizes of the colliding droplets matter. A large droplet overtaking a very small one may simply push it aside in the airflow around it rather than capturing it. Turbulence within the cloud helps by increasing the relative velocities between droplets and the frequency of their encounters. And there is an electrical dimension. Cloud droplets carry small electrical charges, and droplets with opposite charges are attracted to each other, making coalescence more likely when they meet. The electrification of clouds, which we will return to in a later chapter, begins at this microscopic level, in the gentle sticking together of charged droplets. Now we move into colder clouds and into one of the most elegant mechanisms in all of atmospheric science. At temperatures below 0 degrees Celsius, many clouds contain a mixture of 2 different kinds of particles: supercooled liquid droplets, which we have already met, and ice crystals. These two populations coexist within the same cloud, at the same temperature, at the same altitude. And here is the crucial physical fact that drives everything that follows. At any temperature below 0 degrees, the vapor pressure over a liquid water surface is higher than the vapor pressure over an ice surface. Vapor pressure is a measure of how readily a substance evaporates, how strongly its molecules push outward into the surrounding gas phase. Liquid water, even supercooled liquid water, evaporates more readily than ice does, because the molecules in liquid water are less tightly bound to each other than the molecules in a crystal lattice. The difference is small but consistent. At minus 10 degrees Celsius, the vapor pressure over liquid water is about 10% higher than over ice. At minus 20 degrees, it is a little larger still. What this means in a mixed cloud, one containing both supercooled droplets and ice crystals, is that the air is simultaneously in 2 different relationships with the 2 types of particle. With respect to the liquid droplets, the air is exactly saturated. It holds as much vapor as the droplets can sustain at that temperature. But with respect to the ice crystals, the same air is supersaturated. It holds more vapor than ice can sustain. From the perspective of the ice crystals, the surrounding air is rich with excess vapor that is eager to deposit onto their surfaces. So water vapor deposits onto the ice crystals, and the ice crystals grow. As they grow, they remove vapor from the air, which slightly reduces the local vapor pressure. The liquid droplets, now in slightly undersaturated air, begin to evaporate. They give up their water back to the vapor phase, which then deposits onto the ice crystals. The ice crystals grow at the direct expense of the evaporating liquid droplets. It is a transfer of water from the liquid phase to the solid phase, mediated by the vapor phase, driven entirely by the difference in vapor pressure between the 2 types of surface. This process was first described clearly by a Swedish meteorologist named Tor Bergeron in the 1930s, working alongside the German physicist Walter Findeisen, and it is known today as the Bergeron-Findeisen process, or simply the Bergeron process. It is the dominant mechanism by which precipitation forms in clouds at mid-latitudes and higher. In the clouds that produce most of the rain and snow over Europe, North America, and the temperate regions of the world. The rain that falls on a cool autumn morning, the snow that settles in winter, most of it began as ice crystals growing at the expense of supercooled droplets somewhere in the cold interior of a cloud. As the ice crystals grow larger and heavier, they begin to fall through the cloud. Falling ice crystals collect supercooled droplets that freeze on contact, a process called riming, and they collide with other ice crystals and stick together in clusters. These aggregated ice particles, now considerably larger, continue to fall, and if the temperature of the air below the cloud base is above 0 degrees Celsius, they melt on the way down and arrive at the ground as liquid rain. If the air below is cold enough, they arrive as snow. There is also a newer and more intriguing finding worth dwelling on. In laboratory experiments conducted in recent years using a sealed chamber filled with a gas that mimics the behavior of water vapor, researchers have observed something that the classical picture of rain formation does not predict. When droplets fall from a cooled upper region of the chamber, they appear to encourage the formation of new droplets in the region below them. The falling droplets disturb the local conditions, perhaps by creating small pressure fluctuations, perhaps by modifying the local vapor concentration in ways that are not yet fully understood, and this encourages condensation to begin in regions where it would not otherwise have started. New droplets form below the falling ones, and those new droplets then fall and encourage more in a cascade that propagates downward through the cloud. This is a feedback loop that the standard linear picture of rain formation. Vapor condenses. Droplets grow. Droplets fall. Does not capture. It suggests that precipitation, once it begins, may actively encourage more precipitation in the layers below, and that the process of rain formation may be more self-reinformation, may be more self-reinforcing, more cooperative than we previously understood. The research is still at an early stage, and the degree to which this effect operates in real clouds, with their turbulence and complexity, remains to be established. But it is a reminder that the atmosphere, even in its most familiar expressions, still holds surprises. Rain is not simple. It is the product of a million decisions made at the molecular level. Which droplets grow fastest, which ice crystals find the richest vapor, which collisions result in coalescence, and which glance off, and the fact that it happens at all, reliably, over most of the planet's surface on most days of the year is one of the quiet miracles of the physical world. The sky has a structure, not the structure of a building, fixed and permanent, but a structure nonetheless. A layering, a logic, a set of invisible boundaries that organize everything that happens within it. The layer of atmosphere in which virtually all weather occurs is called the troposphere, from the Greek for turning or mixing. It extends from the surface of the Earth upward to an altitude of roughly 12 kilometers at mid-latitudes, somewhat less, around 8 kilometers, over the poles, and somewhat more, up to 17 or 18 kilometers, over the tropics, where the greater heat of the surface drives more vigorous convection. Within the troposphere, temperature generally decreases with altitude, which is why mountain peaks are cold and high-altitude aircraft need pressurized, heated cabins. The troposphere is the layer where the air is warm enough at the bottom to be buoyant, where water vapor is present in meaningful quantities, where clouds form and weather lives. Above the troposphere is a boundary called the tropopause, a thin zone where the temperature stops decreasing and begins to level off or even increase. Above the tropopause lies the stratosphere, where the air is cold, dry, and extremely stable. There is very little vertical mixing, which is why pollutants and aerosols that reach the stratosphere can remain there for years. The tropopause is a ceiling for weather. It is a stable lid on the troposphere, and it is the physical boundary that determines the maximum height of the tallest clouds. With this structure in mind, the logic of cloud shapes becomes clear. Low clouds, those that form in the lowest few kilometers of the atmosphere, where the air is warmest and most humid, tend to be of the stratus type. They are sheets and layers, spreading horizontally rather than growing vertically because the air within them is not strongly buoyant. Stratus clouds form when a large, moist air mass is cooled gently and uniformly, by contact with a cold surface, by slow, large-scale lifting, or by the gradual mixing of moist and dry air. They are the grey ceilings of overcast days, the fog that settles in valleys at night, the low cloud that makes coastal mornings damp and diffuse. They do not produce heavy rain, their droplets are small and their updrafts are weak, but they can produce persistent drizzle, the finest precipitation which forms when the collision coalescence process operates slowly in a cloud with very gentle air motion. Middle clouds, those forming between roughly 2 and 7 kilometers altitude, include altostratus, a grey or bluish sheet through which the sun appears as if through frosted glass, and altocumulus, a layer of rounded white or grey puffs arranged in rows or patches. These clouds form in air that has been lifted to middle levels, often ahead of an approaching weather system, and their droplets may be liquid or a mixture of liquid and ice depending on the temperature at their altitude. High clouds, those above about 7 kilometers, where temperatures are consistently below -30 or -40 degrees Celsius, are made entirely of ice crystals. Cirrus, cirrostratus, and cirrocumulus all belong here. They are the thin, translucent, elegant clouds that Howard described so beautifully, their shapes determined by the wind patterns at altitude and by the slow settling of ice crystals through the cold, thin air. Cirrostratus, when it covers the whole sky, creates a phenomenon visible from the ground, a halo around the sun or moon, a pale ring of light produced by the refraction of sunlight through the hexagonal ice crystals in the cloud. This halo has been recognized as a weather sign for centuries. The old saying, "Ring around the moon, rain comes soon," has a genuine physical basis, because cirrostratus often appears in advance of an approaching warm front and the thickening cloud and rain that follows it. But it is the vertical clouds, the clouds that grow upward rather than spreading sideways, that are the most dramatic expressions of atmospheric architecture. When the surface of the Earth is heated strongly by the sun, the air immediately above it becomes buoyant and begins to rise in discrete columns or thermals. A small cumulus cloud, the kind you see on a fine summer afternoon, white and rounded against a blue sky, is a snapshot of a thermal in action. The cloud marks the altitude range where the rising air is condensing, and its rounded, cauliflower-like top marks the uppermost extent of the buoyant updraft. Below the cloud, the air is clear and descending, returning to the surface to be warmed and rise again. If the atmosphere is unstable, if the temperature decreases with altitude more rapidly than usual, so that rising air remains warmer and more buoyant than its surroundings for a long distance, the cumulus cloud can keep growing. The condensation of water vapor releases latent heat, which adds further buoyancy to the rising air, which rises further, which condenses more vapor, which releases more heat. It is a self-amplifying process, and in an unstable atmosphere it can carry a cloud from a few hundred meters above the surface all the way to the tropopause. A cloud that has grown to fill the full depth of the troposphere is a cumulonimbus. It is the largest single weather structure produced by the atmosphere, reaching from near the ground to 12, 15, sometimes 18 kilometers altitude in the tropics. The base of a cumulonimbus is dark and turbulent, often only a kilometer or so above the surface, heavy with rain and sometimes hail. The body of the cloud is a churning mass of updrafts and downdrafts, with updraft speeds that can exceed 100 kilometers per hour in a mature storm. And the top is one of the most recognizable shapes in nature. When the cumulonimbus reaches the tropopause, it can rise no further. The stable air above acts as a physical barrier, and the cloud spreads outward horizontally, carried by the high-altitude winds. This spreading produces the characteristic anvil shape, a broad, flat, fibrous canopy of ice crystals extending downwind from the top of the storm, sometimes hundreds of kilometers from the storm itself. The anvil is made of ice, drawn out into thin filaments by the jet stream winds, and it gives the cumulonimbus its distinctive profile, a towering vertical column topped by a wide horizontal plume like an enormous hammer or a blacksmith's anvil pressed against the ceiling of the sky. Not all the sky's geometries are violent. Some are among the most quietly beautiful shapes in nature. Lenticular clouds form when stable air flows over a mountain range. The mountain forces the air upward, and as the air rises and cools, it may reach its dew point and form a cloud. But on the other side of the mountain, the air descends, warms adiabatically, and the cloud evaporates again. The air then rises once more as it passes over the next ridge or is deflected upward by its own momentum, and another cloud forms. The result is a series of standing waves, like the waves that form downstream of a rock in a river, fixed in position relative to the mountain even as the air flows through them. Within each wave crest, where the air is at its coolest and most humid, a cloud forms. The cloud has a smooth, lens-like shape, perfectly symmetrical, with sharp edges where the air enters and exits the condensation zone. It does not drift with the wind. It hangs in place, motionless, while the air flows through it continuously, condensing on the upwind side and evaporating on the downwind side. Lenticular clouds have been mistaken for structured aircraft so frequently and so persistently that the phenomenon has its own entry in the literature of unexplained aerial observations. Kelvin-Helmholtz clouds are rarer and more fleeting, but extraordinary to see. They form at the boundary between two layers of air moving at different speeds. When a faster-moving upper layer slides over a slower lower layer, the interface between them becomes unstable. The faster air above pushes the slower air below into a series of waves, and if the conditions are right, the crests of those waves curl over in the direction of the faster flow, like breaking ocean waves. For a brief period, sometimes only a minute or two, the sky is decorated with a row of perfect curling crests, each one identical, evenly spaced, like a Japanese woodblock print of the sea. Then the waves break, the two air layers mix, and the clouds dissolve back into clear air. The same instability, named the Kelvin-Helmholtz instability, after Lord Kelvin and Hermann von Helmholtz, two 19th-century physicists who described the mathematics of it, also occurs at the interface between ocean currents of different densities and at the surface of the sun. The sky in those brief curling crests is showing you a pattern that runs through the fluid dynamics of the entire universe. The shapes of clouds are not decorative. They are the visible signatures of invisible forces: pressure, temperature, buoyancy, wind shear, written briefly in water before the wind erases them. Step back now. Step back far enough that the individual clouds become too small to see, and what you are looking at is the whole planet. From this distance, the distance of a weather satellite, 400 kilometers above the surface, the atmosphere does not look chaotic, it looks organized. There are great spiral patterns of cloud over the oceans, curving arms of white against the deep blue, turning slowly like enormous pinwheels. There are long, straight bands of clouds stretching across continents. There are clear gaps, vast regions of blue where the air is descending and the sky is dry. The atmosphere, seen from above, has a grammar, a set of large-scale structures that recur, that are recognizable, that obey laws. Those laws begin with the uneven heating of the Earth's surface. The equator receives more solar energy per square meter than the poles because the sun's rays strike it more directly. This means the air at the equator is warmer and more buoyant, and it rises. As it rises, it moves poleward at high altitude, slowly cooling, and eventually descends again at around 30 degrees latitude north and south of the equator, the latitude of the great subtropical deserts where descending, warming, drying air creates the Sahara, the Arabian Desert, the Australian interior. From there, some of the air flows back toward the equator at the surface, completing a large circulation loop called the Hadley cell, named after the 18th century meteorologist George Hadley, who first proposed it. Beyond 30 degrees latitude, the circulation becomes more complex and more variable, driven by the temperature contrast between the warm tropics and the cold poles. This is the domain of the mid-latitude weather systems, the depressions and fronts that bring changeable weather to Europe, North America, and the temperate zones of both hemispheres. At the heart of mid-latitude weather is the concept of an air mass. An air mass is a large body of air, sometimes the size of a continent, that has spent enough time over a particular surface to take on the temperature and humidity characteristics of that surface. Air that has sat over the Arctic for weeks is cold and dry. Air that has moved north from the subtropical Atlantic is warm and moist. Air that has come from the continental interior in winter is cold and dry. From the same direction in summer, it may be warm and dry. These different air masses meet at boundaries called fronts, and fronts are where the most interesting weather happens. The boundary between a warm air mass and a cold air mass is not a smooth vertical wall. It is a sloping surface, tilted at a very shallow angle. The warm air always lies above the cold air, because warm air is less dense. The slope of a typical warm front is roughly 1 in 100. For every 100 kilometers of horizontal distance, the frontal surface rises by only 1 kilometer. This is an extraordinarily gentle slope, almost imperceptible if you could see it, but its consequences for cloud formation are profound. As a warm front approaches, as the warm air mass advances and the frontal boundary slides overhead, the warm air is forced to ride up over the cold air ahead of it. This gentle, sustained lifting of warm, moist air over a very long distance produces a predictable and orderly sequence of cloud types, which meteorologists have been reading as a sentence for well over a century. The first sign of an approaching warm front is cirrus, thin, high, wispy ice crystal clouds appearing at 8 or 10 kilometers altitude, perhaps 700 or 800 kilometers ahead of the surface front. The cirrus thickens over the following hours into cirrostratus, the milky veil that produces halos around the sun. Below the cirrostratus, the clouds lower and thicken. Altostratus appears, a grey sheet through which the sun becomes a diffuse bright patch with no distinct edge, like a light behind a frosted window. The rain has not yet started, but the sky has the heavy, expectant quality of a room before a storm. Then the clouds lower further still, the altostratus thickens into nimbostratus, the grey, featureless, rain-bearing sheet that may extend from just a few hundred meters above the ground up to several kilometers altitude. And the rain begins, steady and sustained, sometimes lasting for many hours. This sequence, cirrus, cirrostratus, altostratus, nimbostratus, rain, is not random. It is the direct visual consequence of the sloping frontal surface, the progressive lowering of the cloud base as the front approaches, the deepening of the layer of lifted air. A trained observer watching the sky can read this sequence and know with reasonable confidence that rain is coming in 6 to 12 hours. The sky is legible. It has been legible to farmers and sailors and travelers for as long as people have watched it, though the physical reason for the sequence was only understood in the 20th century. The cold front, which follows the warm front, behaves differently. Cold air is dense and aggressive. When a cold air mass advances, it does not slide gently under the warm air. It shoves the warm air upward sharply, producing a much steeper frontal surface and a much more rapid sequence of cloud development. The clouds associated with the cold front are often cumulonimbus, tall, violent, producing heavy rain, thunder, and sometimes hail, but passing quickly. After a cold front, the air is typically colder, drier, and clearer, with bright cumulus clouds developing in the unstable, freshly arrived polar air. Now, none of this would produce the spiral cloud patterns visible from space without the rotation of the Earth. The Earth spins, and that rotation has a profound effect on anything moving across its surface. An air mass moving from high pressure to low pressure does not simply flow straight toward the low, it is deflected. In the northern hemisphere, it is deflected to the right. In the southern hemisphere, to the left. This deflection is called the Coriolis effect, named after the French mathematician Gustave de Coriolis, who described the mathematics of rotating reference frames in the 1830s, and it arises because the Earth's surface is moving at different speeds at different latitudes. At the equator, the surface moves eastward at about 1670 kilometers per hour. At the poles, it moves at 0. An air parcel moving poleward is moving from a faster spinning surface to a slower one, and it therefore appears to curve eastward relative to the surface below it. The Coriolis effect is what gives low-pressure weather systems their spiral structure. Air flowing toward a low-pressure center is deflected sideways, and instead of flowing straight in, it spirals. In the northern hemisphere, this spiral is counterclockwise. In the southern hemisphere, it is clockwise. These rotating systems are called cyclones, not in the sense of the violent tropical storms we sometimes call by that name, but in the general meteorological sense of any rotating low-pressure system. The curved bands of cloud visible in satellite images of mid-latitude weather systems are the arms of these cyclones, the fronts wrapped around the rotating low, the warm sector of tropical air caught between the advancing cold front and the retreating warm front. When meteorologists look at satellite images, they are reading the atmosphere directly. A well-developed cyclone has a recognizable shape. The cloud-free warm sector, the sharp line of the cold front with its towering cumulonimbus, the broad shield of layered cloud ahead of the warm front. Dry slots, regions of descending cloud-free air, curve around the center of the low, giving the system its characteristic comma shape when seen from above. Every feature of that pattern is a consequence of the same physics. The uneven heating of the surface, the temperature contrast between air masses, the sloping frontal boundaries, the Coriolis deflection. The geometry of the cloud pattern is not arbitrary. It is the atmosphere's rotating fluid dynamics made briefly visible before the system moves on and the sky clears. There are moments when the atmosphere does not feel subtle. A mature thunderstorm is one of those moments. From the outside, it looks like a mountain, a dark, towering column of cloud rising to the tropopause, its top spreading into the characteristic anvil, its base low and bruised and turbulent, lit from within by flickers of light that are gone before you can quite be sure you saw them. From the inside, it is something else entirely, a self-organizing engine of remarkable power and complexity, sustaining itself through a cycle of updrafts and downdrafts that can last for hours. The engine begins with a strong updraft, warm, humid surface air drawn into the base of the storm and carried upward at speeds that can exceed 100 kilometers per hour. This updraft is what drives everything else. It carries water vapor upward, where it condenses and releases latent heat, which adds further buoyancy and accelerates the updraft further. It carries liquid droplets upward into the freezing levels of the cloud, where they become supercooled, and then further upward into the glaciated upper cloud, where ice crystals form and grow. The updraft is so powerful that it can carry hailstones upward repeatedly. A hailstone may be swept up into the freezing upper cloud, accumulate a layer of ice, fall partially, be caught by the updraft again, accumulate another layer, and repeat this cycle many times, each cycle adding a new concentric layer of ice. The concentric rings visible in a cross-section of a large hailstone are a record of these journeys. At the same time, precipitation loading, the weight of all this water and ice accumulating in the upper cloud, begins to drag air downward. The downdraft develops alongside the updraft, carrying cold, rain-cooled air down from the cloud and spreading it outward at the surface as a pool of cold air called the gust front. A mature thunderstorm has a carefully organized structure in which the updraft and downdraft occupy different parts of the cloud and feed each other. The updraft brings in warm surface air, the downdraft exports cold air, and the storm moves forward along the gust front, constantly drawing in fresh warm air ahead of it. Now, to the question of lightning. How does a thundercloud become electrified? The mechanism involves collisions between two types of ice particle in the middle levels of a cumulonimbus, typically between about -10 and -25 degrees Celsius. There is a region where supercooled liquid droplets coexist with small ice crystals and with soft, rounded ice particles called graupel, which form when supercooled droplets freeze onto falling ice crystals, building up a spongy coating of rime ice. Graupel particles are larger and heavier than ice crystals, and they fall through the cloud while the smaller ice crystals are carried upward by the updraft. When a falling graupel particle collides with a rising ice crystal in the presence of supercooled liquid water, a small but consistent transfer of electrical charge takes place. The graupel acquires negative charge and the ice crystal acquires positive charge. This is not fully understood at the fundamental level. The precise mechanism by which the collision transfers charge is still an active area of research, but the direction of the transfer is consistent: graupel negative, ice crystals positive. The consequence of this consistent charge separation is that as the storm develops, the falling graupel accumulates in the lower and middle parts of the cloud, carrying its negative charge downward, while the rising ice crystals carry positive charge upward to the top of the cloud. Over the course of minutes to tens of minutes, the cloud develops a large-scale charge structure, a region of positive charge near the top, a region of negative charge in the middle to lower cloud, and often a smaller region of positive charge near the very base. The total voltage difference between the main positive and negative regions can build to hundreds of millions of volts. The surrounding air is an insulator. It resists the flow of electrical current, but no insulator is perfect. When the voltage difference becomes large enough, the air breaks down. A channel of ionized air whose molecules have had electrons stripped from them, making them electrically conductive, propagates downward from the cloud in a series of steps, each a few tens of meters long, pausing briefly between steps. This is called a stepped leader, and it is largely invisible to the naked eye. Meanwhile, upward streamers of ionized air rise from tall objects on the ground, trees, buildings, hilltops, reaching toward the descending leader. When a stepped leader and an upward streamer connect, the circuit is complete. A massive surge of electrical current flows up the completed channel. This return stroke is what we see as the lightning flash, and its temperature, briefly, exceeds 30,000 degrees Celsius, roughly 5 times the temperature of the surface of the sun. The thunder is the sound of that channel of superheated air expanding explosively outward. Beneath a thunderstorm, on its underside, there is sometimes something that looks like the sky has grown a second, lower surface. A field of rounded, pouch-like bulges hanging downward from the cloud base, each one perhaps 100 meters across, arranged in clusters or rows across the underside of the anvil or the rear of the storm. These are mammatus clouds, from the Latin for breast, named for their rounded, drooping shape. They are unusual because most clouds form from rising air, but mammatus form from sinking air. Pockets of cold, moist air descending from the base of the cloud into the relatively dry air below, cooling further as they descend and condensing briefly into visible cloud before the moisture mixes away into the dry air around them. They are a sign of the violent instability within the storm above, of the powerful downdrafts working alongside the updrafts in the storm's interior. They are often seen after the most intense part of a storm has passed, trailing from the underside of the anvil as the system moves away. Now let us go much higher. Far above the troposphere, far above the stratosphere, at the very edge of the atmosphere where it shades into the near vacuum of space, there are clouds. They are called noctilucent clouds, from the Latin for night shining, and they form in the mesosphere, the layer of atmosphere between about 50 and 85 kilometers altitude. The mesosphere is the coldest region of the atmosphere, temperatures that can fall to minus 130 degrees Celsius, the coldest temperatures found anywhere on Earth. It is also extraordinarily dry. The amount of water vapor present at 80 kilometers altitude is almost unimaginably small, perhaps a few parts per million. And yet, at those extreme temperatures, even that vanishingly small amount of water vapor is enough to form ice crystals on tiny meteoric dust particles, the microscopic debris left behind by the constant rain of micrometeoroids entering the upper atmosphere. These ice crystals are so fine, and the air at that altitude is so thin that the clouds they form are essentially invisible during the day. But on summer nights at high latitudes, above about 50 degrees north or south, the geometry of the Earth's shadow creates a window of opportunity. The sun is below the horizon from the perspective of an observer on the ground, so the sky is dark. The clouds glow with a distinctive electric blue or silver-white light, rippling and waving across the high dark sky in patterns that reflect the atmospheric wave structures at that altitude. They are visible only in the deep twilight of a summer evening or pre-dawn morning, and only from high latitudes, and only when the conditions are precisely right. They are among the rarest and most beautiful things the sky produces. Noctilucent clouds appear to have been growing more common and more widespread over the past century, and this is believed to reflect the increase in methane emissions from human activity. Methane, when it breaks down in the upper atmosphere, produces water vapor, and that additional water vapor at high altitude provides more material for noctilucent cloud formation. They are, in this sense, a signature of human influence written in ice at the edge of space. And this brings us to the deepest uncertainty of all. As the atmosphere warms, as the average temperature of the lower atmosphere rises due to increasing greenhouse gas concentrations, how will clouds change? This is not a simple question, and it is one that climate scientists have been wrestling with for decades without arriving at a definitive answer. The difficulty is that clouds do two opposing things simultaneously. Low clouds, particularly the stratus and stratocumulus sheets that cover large areas of the subtropical and mid-latitude oceans, cool the surface by reflecting incoming sunlight back into space before it can warm the ocean below. High clouds, particularly the thin cirrus and the anvils of tropical thunderstorms, trap outgoing infrared radiation, the heat that the surface radiates upward, and prevent it from escaping to space, warming the surface. Whether the net effect of all clouds together is warming or cooling depends on the balance between these two effects, which varies enormously by cloud type, altitude, and location. In a warming world, the crucial question is whether that balance will shift. Will low clouds become less extensive as the atmosphere warms, reducing their cooling effect and allowing more sunlight to reach the surface? A positive feedback that accelerates warming. Or will they become more extensive, providing a negative feedback that moderates warming? Different climate models give different answers, and the spread in their projections of future warming is dominated more than by any other single factor by their differing assumptions about how clouds will respond. A 2023 study examining the thermodynamics of cloud cover and temperature suggested that a 1-degree rise in mid-atmospheric temperature could reduce cloud cover by between 1.5 and 7.5 percentage points, depending on how atmospheric humidity responds. If that is correct, it implies a significant positive feedback. Warming reduces clouds, which allows more sunlight in, which warms the surface further. But the uncertainty range in that estimate is large, and other analyses reach different conclusions. This is where we slow down. Not because there is less to say, but because what remains is the kind of thing that asks to be taken quietly, the way you take in a landscape from a hilltop rather than from a moving car. We have been moving through the atmosphere at some pace. From a man in Tottenham watching the evening sky, through the molecular machinery of condensation and ice, through the great spinning grammar of fronts and cyclones, through lightning and the edge of space. The water that forms tonight's clouds is very old. Not old in the way a rock is old or the way a fossil is old. Old in the sense of having been on a journey so long and so varied that the word journey barely contains it. A water molecule that condenses tonight into a droplet in a cloud above the Atlantic may have spent the last few thousand years locked in the ice of a Greenland glacier, released slowly as the ice melts, carried by ocean currents to the tropics, evaporated from the surface in the heat of a Caribbean afternoon, carried northward by the atmospheric circulation, and lifted finally into the cloud base where it found, perhaps, a grain of Saharan dust to condense upon, perhaps, a grain of Saharan dust to condense upon. Before the glacier, it may have been in the ocean for 10,000 years. Before that, in a river. Before that, in a cloud over a different ocean, falling as rain onto a forest that no longer exists. Before that, deeper still, in the body of a living thing, a fish, a tree, an insect that breathed and drank and released it back to the world. The water cycle is not a cycle in the simple sense of a wheel turning in one direction. It is a vast, branching, rejoining network of pathways, each water molecule following its own individual route through ocean, atmosphere, ice, soil, and life, over timescales that span from hours to millions of years. The same water that falls on you as rain tonight has, at some point in its history, been part of almost everything. It is one of the most ancient substances on Earth, and it has never been created or destroyed, only changed in phase, moved from place to place, incorporated and released over and over since before the first living cell. There is something quietly remarkable in knowing that the cloud above you carries this history, invisibly, in every droplet. Now, to the question of what clouds mean for the planet's energy, its warmth, its habitability, its future. The Earth is warmed by the sun and cooled by radiating heat back to space. The balance between incoming solar energy and outgoing infrared radiation determines the average temperature of the surface, and clouds intervene in both directions. A low stratus cloud over the ocean is almost opaque to visible sunlight. It reflects perhaps 70 or 80% of the sunlight that strikes it back into space, preventing that energy from ever reaching the surface. On a day of extensive low cloud cover, the ocean beneath receives only a fraction of the solar energy it would receive under a clear sky. Averaged across all the low clouds on Earth, this reflective cooling effect is enormous. It is estimated to reduce the amount of solar energy reaching the surface by roughly 50 watts per square meter globally, which is a very large number. For comparison, the warming effect of all the carbon dioxide humans have added to the atmosphere since the Industrial Revolution is estimated at about 2 to 3 watts per square meter. The cooling effect of low clouds dwarfs the warming effect of current greenhouse gas levels, though of course the two effects are not directly comparable in their dynamics. High clouds work in the opposite direction. Thin cirrus at 8 or 10 kilometers altitude allows most visible sunlight to pass through it. The sun appears slightly hazy but still bright through a cirrus veil. But cirrus is opaque to infrared radiation, the long wavelength heat that the surface radiates upward. The cloud absorbs this outgoing heat and re-radiates some of it back downward, warming the surface below. This is the same greenhouse mechanism that makes the atmosphere warm enough for liquid water in the first place, but operating through clouds rather than through gas molecules. High clouds, on balance, warm the surface. Low clouds cool it. The net effect of all clouds combined, adding up the cooling from low clouds and the warming from high clouds across the entire planet, is a small net cooling. Clouds, overall, make the Earth slightly cooler than it would be without them. But the margin is not large, and it depends critically on the relative abundance of high and low clouds, which varies with the climate. This is why the question of how clouds will respond to warming is so consequential. A shift toward fewer low clouds, or more high clouds in a warmer world could significantly alter the energy balance, potentially accelerating warming beyond what greenhouse gas concentrations alone would produce. Climate models, the sophisticated computer simulations of the atmosphere and ocean that scientists use to project future climate, represent clouds through simplified mathematical descriptions called parameterizations, because the individual droplets and ice crystals within clouds are far too small and too numerous to be simulated directly. Different models use different parameterizations, and those differences produce the widest range of uncertainty in any aspect of climate projection. The question of cloud feedback, how clouds change in response to warming, and whether that change amplifies or moderates the warming, is the single largest source of uncertainty in our understanding of how warm the Earth will eventually become. It is humbling in a way that feels right for a quiet night. We have named the clouds, understood the physics of their formation in extraordinary detail, mapped their global patterns from space, traced the pathways by which they produce rain, and still the most important question about them, what they will do as the world changes, remains genuinely open. The sky keeps its own counsel. But perhaps that is not where we should end. Perhaps the more important thing is not what we don't know about clouds, but what it means to actually look at one with the understanding we've been building tonight. Imagine looking up at a cumulus cloud on a summer afternoon. You know now that its flat base marks the altitude at which the rising air reached its dew point, the precise temperature at which water vapor could no longer remain as gas and began to seek out the tiny particles of dust and salt waiting in the air. You know that inside the cloud, billions of droplets are suspended in slow updrafts, each one a few micrometers across, each one carrying at its center a speck of the world, a fragment of mineral, a crystal of sea salt, perhaps a particle that traveled from a distant desert on a wind that blew a week ago. You know that the rounded, cauliflower-like towers building upward from the cloud's top are the visible expression of buoyant air still rising, still condensing, still releasing the latent heat of vaporization that was stored in the water when it evaporated from the ocean. You know that if the atmosphere above is unstable enough, that cloud may keep growing for hours, building toward the tropopause, developing the internal charge structure that will eventually discharge as lightning, producing rain that will fall and run into rivers and return to the sea. All of that is happening in a cloud that, from a distance, looks like a soft white shape drifting slowly across the blue. There is something in this that is deeply restful if you let it be. The sky is not random. It is not chaotic in the way anxiety is chaotic, with its unpredictable edges and its sense of things coming apart. The sky is lawful. It follows physics that has been running reliably for 4 billion years, through every storm and every clear day, through ice ages and warm periods, through the rise and fall of mountain ranges and the opening and closing of oceans. Whatever is happening in your life tonight, the water cycle is turning. The fronts are moving. The ice crystals in the high cirrus are growing slowly in the dark air above, too fine to see, too cold to feel, patient and ancient and entirely indifferent to the hours. You don't have to carry the day any further. It has already begun to recede. The muscles in your face can soften. The thoughts that were turning can slow their turning. There is nothing required of you now except to let the breath come and go the way clouds come and go, forming from nothing, drifting, dissolving back into the invisible air from which they came. The water molecules that were in a cloud this morning are somewhere else now, back in the vapor perhaps, or fallen as rain, or settled as dew on grass, somewhere in the dark. The cloud itself is gone, but the water is still there, still moving, still part of the same patient cycle that has been running since before the first living thing drew breath. You are made mostly of water. The clouds are made of water. The rain that falls tonight has been in the ocean, and in the ice, and in the air, and in living things for longer than the word ancient can quite reach. Something in you is part of that cycle too, something that moves slowly, that does not hurry, that knows how to be still. The day is already distant now. It is somewhere behind you, fading the way a cloud fades, the way a sound fades when the room goes quiet. You don't need to hold on to it. You don't need to understand it tonight. The sky is wide, the dark is soft, the water is patient. Drift now, if you're ready. Sleep well.